And we're live. Hello, everyone, to today's Tech Excellence session. We are going to hear about Metal-In test-driven development, a dual-target TDD approach by Fran Climent. Fran is a senior R&D software developer at Conspert Discovery and also a technical coach at francliment.com. But before he gets into Metal-In test-driven development, we are Tech Excellence, and our vision is to raise the bar of technical excellence across the world. Our team is still the same. It's Valentina, our founder, and Dani, Alina, and me. We are very, very stoked about our Tech Excellence Conference, which is coming up on Friday, the 22nd of November. It's a live online event. It's completely free, and you can still register on techexcellence.io/conf. Make sure to reserve that date. We have so many great speakers, and if you would miss that, that would be a shame. Our sponsors are Optivem, Moco IT, and CodeArtify. And if you want to improve your technical skills, then check out the content using the QR codes that we have shown on the slides here. You can, of course, join us on Meetup, but also on YouTube, LinkedIn, X, Discord, and GitHub. Again, our sponsor is Optivem, Moco IT, and CodeArtify, and our partner is QE Unit. And before I hand over the mic to Fran, I want to remind the audience that you are very much encouraged to write down any question you have in the comment section below, and we will take that up after Fran's session and discuss it all together. But now I hand over the mic to Fran. The stage is yours.
Thank you. Thank you, Oliver. Thank you, team, for making these things possible. You are really rising the bar. Thanks for all of you behind there listening. And yeah, the talk is called Metal-In test-driven development, right? And we are going to talk about the embedded. But maybe you know something about me because Oliver has made the introduction. But I will need to know something more about you. And I want to make you a couple of three questions. Let's try if I can manage my slides. So the first one is to know where do you come from? Are you an embedded developers or not? You have here a QR to join the Slido and make the voting if you can do it. Let's see what we get. Nobody? Hello? Okay, we have one, at least one person. It's important because I have tried to synthesize several things that come from the embedded. And it's sometimes it's difficult because we talk with from things that are really special. Maybe people from other technical stuff don't know about it, but I have tried the presentation to be understandable for all of us. But I would like to know it. So I'm going to go forward. I have only 6 of you voting, but it's what we have. Not too much. We have to go ahead. Let's see for the next questions. So yeah, we have almost half. Well, probably. So we have people from the embedded. That's right. Great. So the next one will be, do you know what TDD is all about? If you are familiar about it or not. Independently if you come from the embedded realm or not. So if we have more than 7, will be better, but yeah, we have 8 people here, there. Great. 10. Okay. It's not 11, not representative, but we can go ahead and take a look at the next one. But first, the results of this one. Yeah, okay. So we have a great thing. It's almost 80% of you, the ones that have answered, is know what TDD is all about. That's great. And now comes the key. Well, maybe it's not the key, but it's a key question. Do you practice TDD at work? Yes or no? Maybe if it depends, is from time to time, it will be a yes. And if you don't practice, never, it's no. We have the 10 than before. Let's go ahead. 11. Oh, what a figure. So yeah, that's great. That's great. 91%, it's using it, almost all of you. That's a great thing. I think it's not the thing that, in my experience, is not what happens in the embedded. But anyways, it's a great figure. But these two questions, even the title of this talk, maybe it's wrong, because we are aiming into a possible solution that we could end adopting, like using TDD or not. But we haven't asked or thought about the proper questions, because something that is a little bit higher in abstraction will be like how many. Will be how much time, for example, does it take since we have an idea till it's finally working on our product, or discard it because it was wrong. That's what means learning fast, right? How many lines or how many changes have we made since the last completed run? Or, for example, do we have any difficulties to comprehensively test whether those ideas are working as expected, as well as our previous ones keep working as they were? These are more proper questions. And in my experience, I know firsthand that the differences out there are really huge. They range from hundreds of lines, lasting days or even weeks, by having to deal with several kinds of hardware in the loop, till a single line of code in less than a minute by only using our development environment. And the differences are not strictly related, or are not strictly related in how hard is the product that we are building. It's essential complexity, but they are mostly related with how our development processes prevents us to combat the accidental complexity mercilessly. I'm going to share you. Well, I started as a hardware engineer back in 2007, but soon I moved to software and firmware, and most of this time I was barely surviving. Right, I'm going to share something that happened to me in 2009. We were developing fully electronically controlled small wind turbines. I was in charge on the embedded software control. We had a small wind tunnel in our facilities when we were able to put the small wind turbine to work and test most of its dynamics, but not all of them, because there were certain situations like when we were facing really huge gusts of wind, really strong gusts of wind, we were unable to reproduce it. And due to this reason, we have been working really hard to have a final release ready, because in 2 weeks, a strong windstorm was arriving to our test facilities. And we have to have everything ready because, we had to have the product facing the wind and test all these corner cases. 2 days before the D-Day, my manager came to my desk and asked me a totally fair question. It was like, Fran, is it going to work, right? Fair question need to be answered with honesty. I said, yeah, I hope it will. And he cut me, he said, hope? He cut in me mid-sentence. It looks like you don't have control about what you're doing. And he was right. Even having done my best, I was completely unsure, because I had nothing in my hand beyond code reviewing and hope. I guess you know what happened when the wind turbine arrived. When the windstorm arrived, sorry. The wind turbine entered into an improper control loop due to a bug. It accelerated beyond its nominal speed, and it broke down in pieces. My code happened to be mere dust in the wind. But it was a lucky event, however, because during the next months, I had a recurrent nightmare in which this event was happening in a wind turbine installed in a schoolyard. And yeah, those words, like, you don't have control about what you're doing, keep resonating in my head during the next coming years, like a splinter in my brain. But how on earth could I have managed to test those corner cases without having to have the full system facing these strong gusts of wind? Really difficult. And looking for answers to these questions, back some years later, in 2016, I got aware of TDD existence. And the strange or the funny thing is that neither my colleagues nor my technical managers have heard about it, have heard a word about it. I think that nowadays it's a more known technique, or at least it's an acronym that is more well spread, but I still deeply believe that is a completely underrated technique in most development environments, and in embedded even more. So my goal for today is to try to show some of its main benefits in action, and you will judge later if I have accomplished my goals. So yeah, this is me. As I said, I started as hardware engineer. I moved soon as a software and firmware engineer. You can follow me I'm quite active in LinkedIn, Twitter, and also my webpage. As Oliver mentioned, I work as a senior R&D software developer at Kongsberg Discovery Spain. But I also, as a technical coach, I rule my own company and help teams to improve their development processes somehow. So, yeah, but why another talk about TDD, right? Why? Well, in this talk that I delivered in the past, I presented the major impediments or roadblocks that I have found in the embedded development realm. And in theory, like all the things that I have seen that are wrong, but present talk can be seen as this practical companion. So I will try to show some of the design decisions, some of the challenges that we can face when we are following it. So without further ado, let's start. And let's start to reviewing which are the common approaches that we usually follow to get feedback from the hardware, that call it the metal. But by an easy example, it's like, how could we assure the code does really turn on and off an LED? It's a really easy question if you come from the embedded, right? It's like hello world. And the common approaches that I have found for this thing lay into one of these categories. It could be like measuring the voltage at the GPIO, or measuring the current loop, using a logic analyzer, or even using some kind of photodetector, external photodetector. And yeah, all these approaches have something in common. It is that additional hardware needs to be added into the embedded development loop. And for sure, we are embedded developers, right? And for sure, we will need the hardware in some moment to try it. But I deeply believe that we should rethink when do we want to let it into our development processes, into our software development processes. And here is where the Metal-In development approach comes to the arena, comes to our help. The main goal is to make possible to create and evolve any embedded code aspect much faster and safer, iteratively and incrementally. Yeah, nice. But how are we going to do that? This is something that is going to be really key. It is going to be our cornerstone for us, by continually looking for ways to get feedback faster, always looking for ways to do it better. And in order to do that, what we are going to do is to treat as much embedded code as possible as an independent subsystem. And I'm going to try to explain what I mean with that. None of the approaches, the previous approaches, is giving us proper feedback about how the embedded code is really behaving. Because short circuits, open circuits, bad soldering, fuse loads, all of them have a really impact in the voltage, electrons, and photons involved, or that we can get in the process. But none of them has a direct consequence, is a direct consequence of the embedded code behavior itself. I'm going to show you in another example what I mean. Imagine that we want to develop a dual axis solar tracker, is the one that we have on the right. we have the solar panel and we have two independent movements, right? In order to do this, we will need 4 sensors to sense the real world, basically, and one in each of these corners of the solar panel in order to know which is the light that is being impacted by the solar panel. And we will have two kind of actuators, 2 motors that will move in the 2 directions. So how it works? How does it work? How could we test, or how do we test that the embedded system works? And you can see here we have something that some electronics that we call it the sensor signal conditioners. They pick the values from the inputs and convert to voltage in that case. So here in this point we have the voltage that is dependent on the light received by each of the sensors. These voltages, those voltages are entering into analog digital converters. And these analog to digital converters, what they do is to convert this voltage to counts, right? In binary. And our embedded code uses them to know which is the light in each of these points. And with some algorithm, it will decide through the port D in this case, so through digital outputs, how to actuate with the motors, right? Which motors should be actuated. And as you can guess, in order to assure that the behavior works, we will need several things apart from the embedded code, right? When we test this thing, we are not only testing the code, we are also testing the hardware, and it's also the motors, right? And a part of that, imagine that we have also incoming communication from third-party systems, and we also are commanding other systems through outgoing communications, right? So this is something how could we treat the embedded code as a subsystem, independent of all the other hardware that we have? That is the key, right? How could we achieve this thing? And in the way that we are going to achieve it is by, whenever possible, there are cases in which it's really hard to do it, but whenever possible, we are going to promote using chip software in the loop, also known as test double, instead of any kind of hardware in the loop. And this chip, because there's something key here. This is the key. Absolutely nothing happens outside the microcontroller in the real world if it doesn't change a special function register bit. Nothing, even those strong gas or wind that I have been talking about. And if we take this into account, we could put our embedded code into a kind of matrix in which the test doubles we could interact with some test double that will put the values in these special registers at our convenience, resembling what's happening in the outside world. Because the embedded code doesn't know from where it comes. It only knows which is the values of the special function registers. So we can use really cheap test doubles to do that. And if we do this, then the test suite can go from metal to metal. It's like end to end. So what does it mean, end to end? In reality, it means from the inputs from the microcontroller that are reaching the embedded code to the outputs. That's the end to end. It's like treating the embedded code as a complete subsystem. Because there's something that we have to notice here, is that the rate of change of the embedded code is bigger than the rate of change of the remaining of the hardware. And additionally, the hardware changes by reasons that have nothing to do with the reason that are provoking the changes in the embedded code. So we have to take this into account. And which is the outcome? Yeah, for sure, we will have better architecture. We will have better code. We will be happier. But this is a really low level details. What really matters is a business outcome. Is that we are going to have an increased embedded development lead time. This is the only thing that matters at a sustainable pace. And as probably most of you have already guessed, we are going to follow an evolutive design and development. And specifically, we are going to embrace the one that you can see in the slide, the one that acknowledges our limitations and divides the development in 3 strategical steps, differentiated steps, known as the make it work, make it right, and make it fast. During the make it work phase, we are focused in trying to solve the problem, not about engineering the code right. Easy. During the make it right, we are focused in trying to engineer and craft the code right in order to make it easy to understand, maintain, and evolve. And in the last step, last but not least, is make it fast. That means fulfill the system timing requirements that we have. One of the problems that I have also have encountered in embedded, it's really common, is that we usually go directly to the third one because we are embedded and we have to do everything really fast, right? And this is the global performance pre-optimization trap. We usually follow in this trap because we go to the third step, which makes the first one, to make it work, even harder. And once we reach this stage, the code is so obfuscated that it's almost impossible to achieve the second one and make it right. So the best evolutive design and development implementation that I have found is by following the TDD. If we follow its microcycle, the red-green refactor microcycle, we will be transitioning among these 3 differentiated stages several times per minute, as we will see in the example. And it's really important to revisit why are we following TDD. Why? Yeah, TDD microcycle in a nutshell. So the first thing that we need is to enter into the red phase. Why? Because we need to be sure that our automated cause-effect relationship checker works properly. And the rule here is to do not write no production code except to make pass a failing test. Why? Because when we are following test-later approaches, what usually happens is the liar anti-pattern. It's like we think or we believe that we are testing everything, but in reality, we are not, right? It's like the picture of this snapshooter. So once we are in red, the next thing that we need is to go to the green, right? Make it work. And the rule is to write only enough production code to pass the failing test. The reason is to have this code working on purpose without uncovered behavior and with minimum accidental complexity. That's the goal. We don't have to introduce anything else that is not needed to make this test to pass, because if we do that, we could also lay into the test layer anti-pattern. We have added some behavior that is not covered by our test, and maybe we think that we are covering, and no, we aren't. Mutation testing is a great tool to unveil this thing. And in the refactor phase, the rule is to change the code structure and not add or change any external observable behavior. And we do it to remove accidental complexity that we have been creating, and we were unable to do it in the red to green, and also to manage the dependencies properly. Fine. So I explain it there because usually I find some people say, no, but we can get the same benefits with the following a test data approach. And no, it's completely different. It's a complete beast. We cannot get the same benefits following a test data approach. So Metal-In test-driven development encompasses the well-known embedded dual target TDD workflow stated in James Guinness' book, in which the same code is run in 2 different platforms, the final running target and the development host. What Metal-In TDD does emphasize is to treat as much units of behavior as possible covered from metal to metal. Units of behavior, end to end, you remember? So as we have said several times, the reason to have a new test is a new behavior, not because we have something, a module or a .c, a new .c. No, it's because we have a new behavior, end to end. And for the embedded code, when we follow Metal-In, we are going to treat the end-to-end is going to, from microcontroller inputs, like can be seen sensors, asynchronous events, incoming communications, till its outputs, like could be seen like digital outputs or outgoing communications, and all of that having the time intro control, right? Because we have timers. We have timers in our embedded simulator. If you use it, we can see it later. We can also rule the time. So in the best scenario, we will be able to both verify and validate that our understandings of the data sheets are correct. That's what we are going to see in the example in the stages 1 to 3. And there are some examples in which we are not going to be able to validate them till we reach the real hardware. Like, for example, imagine that we have a microcontroller talking with an external iterative circuit. We can follow the data sheets of the microcontroller and the external iterative circuit, but until we have it really running in the hardware, talking with the real IC, we cannot validate it. Maybe they are wrong, but if we have test-driven it, all our assumptions are written down, and it shouldn't be any deviation from those assumptions because we have verified. So it's a way let's take a look at what we thought about the datasheet. Maybe we are wrong, and it should be written down, even in the worst case. So yeah, and when I was thinking about which example to show the technique, it's like, yeah, it should be something that is not a toy. It should be something complex enough to show which are the movements that one can do in the real work. Because most of the examples that we usually encounter with TDD are like a toys. It's like, yeah, it's only a class or only a module without any relationship with third-party entities. True. But at the same time, I didn't want it to be a problem that is complex, because the thing with the example is to show the way in which we could solve problems, easier or complex, in a different way. So what can be better than use our kind of hello world, right? Is our beloved LEDs. And this is the kata. This is the example. I call it the 4-level battery monitor. We are going to use 8-bit mere metal microcontroller in C. I choose this environment because it's a really constrained environment, and I wanted to show you that these things can also be done in really constrained environments. The current hardware variant is the one that you see in the image, is using 4 status LEDs to show the battery level connected to the port A's high level. This example belongs to a bigger workshop that lasts almost half a day, and due to the time, we are not able to see all the workshop in action. So the part that comes from the analog inputs till the logic, the controlling logic, are going to be we are going to use a test double for it. We are not going to see it. We are going to see from the outgoing part. So once we have the battery level, what do we do with the LEDs? So we are going to pretend that this microcontroller is the first internal usage of the microcontroller in the company. We're going to pretend that. And that means that we don't have any PAL implementation, nothing. And also we're going to use a module that is called battery status percentage provider. We are going to pretend that this module is being developed by another team, and this is the one that we are going to use a test double for it. The objective, right? The objective is to develop a highly decoupled and portable battery monitor module following the Metal-In test-driven development. And what I mean with portable, those of you that came from the embedded know that we have faced something that it has been called the semiconductors shortage. And what happened is that we have been unable to change one microcontroller by another because we get out of it. And that's really, it's, you know, for example, we talk, there are several certain development environments when for example, the web or the databases are now considered as a mere I/O devices, right? And they are not core, nor they are not centric of our architecture. But maybe we should rethink that a microcontroller is simply a running detail that shouldn't be centric to our architecture. It's something that we should be able to change with barely non-effort or little effort. So let's try to do it. So before starting, this is the this is the environment that we are going to use. We are going to use, simply because this is the environment, the fastest environment I have found so far for embedded C. I'm always looking for faster ways to do the things. It's the key constant for us, you remember. So we are going to use Seedling as the lightweighted unit testing for C. It's really tiny and is able to be loaded and flashed in really limited microcontroller. So we will be able to flash it into a microcontroller, even this is a bare metal 8-bit microcontroller. One additional feature is that it has the test double creation available. Really nice, we will see it. As the IDE, we are going to use C-Lion, mainly because of the its state-of-the-art automatic refactoring features. I have found any vendor tool that aims into that direction, and this is something key for us. It's going to be key for us. And when we're talking about we are talking about the vendor agnostic tools. The tool chain that I have used is GCC, but it really doesn't matter. We could use any other, like Clang or whatever. And when we talk about the current vendor, is because we, as I said, we should be able to change it, to change the hardware, to change the vendor. But the one that we are currently using is the microchip. So we are going to use its cross-compiler, and something that is really interesting is a simulator. So microchip provides a simulator that is able to, well, it simulates or most of its microcontrollers, supports most of its microcontrollers, and a simulator should be should be a tool that we should ask the vendors to provide. So now, yes, let's take a look at the contracts, specifications, our beloved data sheets. This is the closest thing to a written in stone specification, even though the stone is made of silicon, right? So if we go to the microcontroller that we are using, and if we want to activate the port A, we will see that writing in the port A, in the corresponding bit, will activate this GPIO. So putting a 1 there will mean that we are activating this GPIO, and putting a 0 there will mean that we are setting it to low. And if we want to read, which is the value in the GPIO, it states that also reading from the same port will give us the actual IO pin value. So with these two things, we have almost everything to start. So let's start. Let's start, and this is here you can see, come on, wait a moment. Oh, wait. Yeah, here you can see the environment in action. This is the test suite that I have created. Here you can see I have created some assertion functions, some helper functions, and here we have the common setup and tear down methods that are usually present in any XUnit framework. And here we have several methods of functions. Each of them is an independent test. I have tried to follow the given, when, then structure in order to explain what they do. And each of them is covering a specific corner case following the boundary value analysis. And each of these corner cases are defining an interval of behavior, also known as a partition. So in those intervals, some special behavior is present. If we go to the first test and run it into the target, we are going to wait till it's finishing, taking into account how many time it takes, and later I will explain what has happened behind the curtains. One thing that I want to mention is that all the tests are currently ignored. So if everything is fine regarding the framework, it should pass. Everything should be green. It's almost finished, and here it finished. 27 seconds. Not bad regarding what we are used to face in the real world, in embedded. But let's take a look at what happened behind the curtains. What Seedling did for us is it created the test runner for us. It cross-compiled using the cross-compiler. it also cross-compiled the test suite itself, and using the cross-compiler for sure, and it linked everything together, generating the binary executable that is able to be run into the microcontroller. But as I said, we don't have a microcontroller, we have a simulator. So the next thing that it does is loading this binary into the simulator, and it makes the output char. So the results of the tests are written through the output char method, that it's written into a specific UART of the microcontroller. And what it has been done is the output of this UART is diverted to a common text file, and at the end of the test, the contents of these text files is the one that we take as a results. And here you can see these are the results coming from the microcontroller through the UART, and you can see that it lasts 8.67 seconds to run of the 27, and the format is a G-test format. That's why C Lion is able to know what's happening behind the cortex. So let's go for the first test. Let's trying to enter into the red state. As you can see here, it's making the port A, it's making a mask with F, the high level of the port A, and is asserting that is 0. So it's asserting that the high level, the 4 bits, higher 4 bits of the port A are high. Low, right? So what can we do to make this test pass, to make this test fail, to enter into the red? So the minimum thing that we could do is to put all of them to high. If we put all of them to high, and later we test that they are off, it should pass, right? Let's do that. Let's run it in the hardware. Let's run in the target. I have speeded up a little bit, not 27 seconds or more, and as you can see, it's passing. So for some reason, we have been unable to put these GPIOs to high because the test is passing. And yeah, but are you sure? Maybe we should take a look in the hardware. So yeah, let's do that. Let's flash the test runner into the final product. There, we are flashing it. And see what happens. Now we are flashing the hardware. You have it. This is the usual rhythm that we are used to have when we are dealing with external hardware. Or it gets even worse. As long as we put more hardware into our development loop, it gets slower and slower and slower and harder to reproduce. I guess you know as better than me. And yeah, they are effectively off. So there's something in the datasheet that we have not understood correctly. We are not able to run it into the hardware. So if we take a look at the datasheet, a closer look into it, we will see that we will need, there are a couple of additional registers involved, TRIZ-A and ANSI-A. In order to, what it happens is that after reset, all these ports are in high level. That means that after reset, all the GPIO, all the GPIOs are configured as analog inputs. That's why we have been unable to command it. So if we take a closer look in the datasheet, we will see that in order to do it, we need to set the TRIZ-A corresponding bit to 0 in order to activate the output driver, and also set the corresponding ANSI-A bit to 0 in order to activate the input buffers. The combined effect that when we do that is that this GPIO, I say later before digital input, this GPIO is going to be configured as a digital output. So let's do that. We have something missing, so let's do it. Let's set this GPIO as the port A, as everything on the port A, put it as digital output. And if we do that, you can see that now it's failing. And it's failing by the reason that we were expecting to fail, because it has not been activated. That's nice. So yeah, but yeah, let's see it in the hardware, because we need to see, we are used to seeing lights for believing. Let's flash it again, and now they are on. So yeah, we have been able to do it. Now it's failing, and now we have entered into the red phase, right? We are assuring that we have understood what is needed to be done in the metal, in the hardware. Now is when we need to do it to make it work as fast as we can. So which is the minimum implementation to make this test pass? The minimum thing that we can do is to, yeah, if we put all of them to low, it should pass. And yes, it does. So we have been able to put it to low, because at 0% of battery, all of them should be off. That's the test that we are dealing with. And if we flash it into the hardware again, the final product, they should be off. And they are. This is going to be the last time that we saw the hardware into our loop, our development loop. I have used it only to show you that effectively we are dealing with the LEDs properly. So, yeah, we have made it work. But as close to the metal as possible. We are using special function registers. Now is when we need to make it right. Now is when we try to put in our business or domain logic. It's time to engineer the code a bit, right? That's what we are going to do now. So, what's wrong here? So, here, this code doesn't belong to the test suite. It's a production code, right? So let's move it. Let's use the IDE and create the proper method for it. BatteryMonitor update status. We are going to call it in that way. Yes, you can see it has created the definition and implementation, and we are running the test again. And they are passing. Great. Also, now we can move it because it's still there. It's still in the test file, test suite. Let's move it to the proper method. Let's extract or move it to the proper module. It is the module, the BatteryMonitor module that we are trying to create, right? This is the production code. Let's move it there. Yes, move it. Okay, it has been moved to the test file, to the test folder, sorry. Sorry for that. We are going to move it there. Let's copy this module into the entities folder, in the source code folder, production code, sorry. And let's put the source file and the header file there at our site. Yeah, and if we run the test now, they are passing. Great. But take a look at these include files. They belong to the testing framework, and they shouldn't be there. As everything that is included, all the dependency that we have to manage. They need to be there for a specific reason, and this shouldn't be there. Let's remove them, and let's run the test again. I don't know why the IDE they put it there. And this include over here in the line 5 is because this source file is the one that is implementing the API, specified in the BatteryMonitor.h. So yeah, it passes. Great. Now let's go to a complete microcycle in action again. So here, let's go for the next test. The one that says that 24% all status LEDs are off. Let's copy paste the arrangement, copy paste. Ooh, be careful with that. So we are saying the same. All the port A enable is high, and everything should be not off for sure. Yeah, we are in red by the expected reason, which is the minimum implementation to make this test pass. Putting all to off, to low unconditionally will make the trick. What about calling the production code the same way it is? Let's see. Yeah, it passes. Great. Look at this time to refactor. Look at these 3 lines. They are here repeated, right? And these 2 lines are really low level details. I have to explain you what they mean. And they mean, so it's a good thing to, yeah, this knowledge that we have in our head, put it in a proper method. These 2 lines mean given the port A GPIOs are all outputs. Let's do that. Let's run the test again. Yeah, it passes. Let's move the implementation to the back of the file. We don't want really low level details in the middle of the tests. Let's run the test again. Well, or let's remove the duplication in the other test and let's run the test again, and they should be passing, not rocket science. We have hidden a little bit low-level details. And what about this sentence? It's also a really low-level detail. This sentence means that the given the port A high level are all on. So let's do the same. Let's put this knowledge into a method, run the tests, put it to the back because it's a really low-level detail, and we can mark that this section is a custom given section. And yeah, this method, so this is there. We have removed the duplication and we run the test again. We should be green because we are refactoring, and yes, we are. Great. Let's take a closer look to our dependencies. And we can see there is a sim that enables to import the MCU package when we are running in the target. And you can see that we have the battery monitor and the test battery monitor, and both depend on the microcontroller package. They are crossing a hardware boundary. It should be an architectural boundary, but it isn't, unfortunately. And these red arrows are the ones that make these two modules firmware. They are firmware because they depend on something that is hard to change. In our case, it's the microcontroller unit. So we could try to address this issue now in the current refactor phase, but we are not going to do it now. I'm going to continue adding more behavior. And some of you could be asking why? Because we are following TDD in that, and we are the ones who drive, right? And in this case, it was me. I decided to do it in that way. That's the only reason. So let's continue. So let's go for the next test. The next says that 25%, then only one LED should be on. So let's copy the arrangement, setting the port A GPIO to outputs, and here I'm setting the port A to the binary complement of the expected output. And if we run the test, it should be failing because LED 4 is not on, just by the reason that we were expecting. We are in red. Yeah, so which is the minimum implementation? This test is the one that is going to force us to ask with the battery, to ask the battery percentage. We cannot fake it anymore. So we could now use the test double, the one that we are talking about, this battery charge status provider, get charge percentage. And we are going to include here a mark that is being used, is a collaborator. And if we run the test now, for sure it's going to be broken. The build is broken because, there's no implementation for this method. As I said, we are using a test double for it. So the way we need to use a test double, the way that this is done in the seedling is by including in the test suite, including the same API, the same module, same header file at the end of the row, but putting the word mock in front of it. If we do that, the framework is going to create a test doubles automatically for us. And now it's failing, it's still in red, but not because the build is broken, but because now all the three tests are failing, even the ones that were passing before. And the reason is because that mocks. The reason is because seedling by default uses strict mocks, and mocks, as we know, knows too much. That's why everything has been broken. But anyways, we are going to use mocks, but we are going to hide them really quickly. We will see it later. But by the way, let's put the expectations in order to make this previous test pass. Let's go to the first one. And the expectation which is done with CMOC is by using the same method, followed by expect and return, and setting which value do we want to return from the battery. In that case, it will be 0. Now it's passing. Let's do the same with the 24. It should be passing. And now, let's see, is the only one. The only one that is failing is the test that we were dealing with. And let's put its expectation. It should be 25. And if we run the test now, it should be failing by the reason we were expecting to fail. And it's because LED 4 is not on. So we are in red. Minimum. We need to go to the green. Minimum implementation. I think that you will agree that the minimum thing that we can do is to, if the battery is 25, let's activate the LED 4, else let's clear them all. And if we run the test now, yeah, it passes. We did it. Great. So, time to change the code a bit, right? Let's do a little bit of refactoring. Look at this line. Okay, let's see. Look this line. This line is a really low level detail. It knows too much. It knows that we are not using, it knows which module are we using to retrieve the battery. It knows that we are not using its production code, but a test double for it. And it knows that we are using a mock for it. And it also knows that we are using CMOC too much. So what if we could do this thing? We can extract this method and say, there's given the battery charge percentage status, is I'm passing the desired battery percentage. If we do that, yeah, passing the, and we extract this method, and we could pass the desired battery to the mock itself. We have, yeah, it should be, we are refactoring, we should be passing, right? Oh, but no, it's failing. Now it's failing. Oh, I screw up. Okay, now it's 25%. That's the things, yeah? Defect localization. Whatever it is, it was really, really near to me. Maybe some lines after, a couple of lines. So now it's passing. Now we can move the implementation to the back of the file, low-level details. Yes, and mark that is a give custom arrangement section for it. And yeah, if we go run the test now, it should be passing. Yes, it is. So let's use this proper arrangement method in the other ones. Hiding the thing, we are putting a sim in which we are hiding the way in which we are retrieving the battery. And that will allow us in the, we are not going to see it today, but in the future, we will be able, to, it's going to be repeated, sorry. We will be able to change this mock that we have inside this method, change it and use slightly by slightly reach the real input of the battery using the real code. That's the key thing, right? So it gets cleaner. So closer look to our dependencies. As you can see, we have here the battery. So now the battery monitor and the test monitor depend on the collaborator, the battery charge status provider. And we can see how the test suite is instantiating and creating the test double for it. The hard to change dependencies are still there, the same way they were. So let's continue. If you remember, each test suite run on target took 27 seconds. And we need to go faster. We need faster feedback, especially when we want to use mutation testing or we want to do pair programming or assembly programming. We get shorter and shorter and shorter. And this is one reason. And the other reason is because we will have better other tools available. We will need to use it in the host. So let's try to run this test, the same test, in the host. In the host, we are going to use GCC. And yeah, it fails. It fails because we are not incorporating, we are using GCC, and we are not incorporating any microcontroller package. And due to that, for sure, the host doesn't know what the port A, ANSI A, and trace A are. So how can we fix this thing? And here, one way to do it is by applying the separation of concerns. Because one thing is assuring which values are written to or read from a specific memory address, and the other complete different thing is assuring that the address is located where the special function register is. So if we take this into account, we could use really cheap fakes. When the tests are running in the host, the framework activates this flag. And if we are running under the host, we could say that the port A, trace A, and answer A are simply 8 bits values. And we have defined it there, but we need it to access from the test suite. So we are going to use accessing these globals. Yeah, all globals, bad thing, but yeah, it's going to be momentarily. So if we do that, we have created these fakes, and you can see the build works and is running the tests now. And here we will see how much time does it take. 10 seconds. It's almost a third of the time that it took on the target. We are getting faster. And as I said, we will have several tools available, like mutation testing, sanitizers, whatever is present, it's available in plain C. It will be at our disposal, and as well as, for example, the code coverage. As you can see here, we have the code coverage. And so we are going to be running in the target because it's a little bit faster. And from time to time, we are going to change to on the host. And from time to time, we are going to change it to the target. So, yeah. When we run it in the target, these are our dependencies. As we can see, the BatteryMonitor depends on some globals. And yeah, if we have run it in the target, now is able to run in 2 different platforms. That is a precondition to have something that is portable, but our code is really portable? No, not really, because it depends on some globals, like the port A and trace A and answer A, that are really low-level details that belong to a specific microcontroller. So even though we are running in the host, we are still depending on the microcontroller. We are still firmware. So let's keep now by running the test suite on the host, and let's see what we get. The next test is the one that says that at 49%, we will have the LED 5 and LED 4, LED 4, at 49%, only LED 4 is going to be active. So let's run the test again, and it should fail because the LED 4 is not on. Yes, it is. So one thing that we are in red, time to go to the green. We are going to follow now a technique that allows us to have some coupling between the production code and the test code. Its name is coined as triangulation, and we are going to use these concrete specific values that, for example, the 25 that we have on the right and the 49 that we are now dealing with define an interval of behavior, and we know that it's going to be a bigger or bigger than or less than in some way, but we are not going to use this generalization yet. We are going to use the triangulation. So the minimum thing, if we follow triangulation to make this test pass, is to say if it's 25 or 49, deactivate the LED 4, and it passes. Great. Next one. We are going to the one that is at 50% of battery. Now LED 5 and LED 4 should be on, and the C in hexadecimal is the binary complement. So let's call the production code and run the test. It should fail because neither LEDs are on, and which is the minimum implementation to make this test pass. Okay, you will agree that if you say the battery percentage is equal to 50, let's activate both LED 5 and LED 4, and if we run the test, we should be passing. Let's see, but no, it doesn't work. Okay, why? Okay, I forgot to activate the LED 4. That's the reason. We are getting closer. Now it passes. Okay, so now we are going to follow this triangulation stuff till we have all the corner cases covered, following this if-else and the triangulation until we have everything ready before we try to remove this, to put this generalization in place. And here we have it. And once we have it, it's important. Yeah, let's run it in the target. Don't forget that. We haven't done anything strange, but yeah, two different platforms. Maybe there are something different. No, they are passing. Great. Now it's time to refactor. So if now we can put the generalization in place slightly, step by step, in that way. And if we screw up in some moment, as long as we have all the corner cases in place, the test suite, the testing framework will alert us. As you can see now, I have screwed it. Now, it should be equivalent, and it is. And we can also invert the order of this if-else statement and run the test again. And it passes. This else is redundant. Let's remove it. It passes. Oh, and now these things are also redundant, these check-ins. We can remove them too. Let's see. Yeah, it is much cleaner, much simpler. So now is where we are going to try to remove the dependency on the microcontroller. Let's do that now. This is the shape in which the current production code is. And as you can see, there is a sentence for each of there is a single sentence in each of the corner cases. And this is because we had the 4 LEDs. In this current variant, we have the 4 LEDs connected to the same port in the high level. And this has been the easier and fastest way to do it. But for sure, we cannot say to our hardware colleagues, okay, you are tied to use these GPIOs, you are not able to use any others in the microcontroller. So we will need to be able to deal with each GPIO individually in order to have this freedom. And at the same time, if we do that, we could extract and we can create an abstraction in which we could try to deal with each of these GPIOs independently and without knowing which microcontroller is behind the curtains. But in the way the code is, in this shape, this is going to be really hard. So what we are going to do, we are going to first make the change easy. So we are going to make a kind of refactors in order to put the shape of the code in a proper status to then make the easy change. So what we are going to do is we are going to change each of these sentences by its equivalent while they are dealing with each of the GPIOs individually. What you see there is the common masks that we are used to use in embedded, right? So slightly by slightly, adding each of them one by one, and assuring that we have not broken anything. It's always faster in that way. So let's run it in the target now, and it runs. So we have accomplished it. We have made the first step. Now is when we are going to try to make the easy change. Let's call it easy. We will see. Okay. Here you can see that we have two different types of sentences. One of them, this one, sets or puts 0, a low level in a port A bit 4, in the port A fourth GPIO. And we are going to extract this sentence behind a method that we are going to call pal GPIO low. Well, the two sentences that we have. One is to clearing the given GPIO. The other one at line 21 is setting or putting to high. Now we are going to extract this line in 16 into a method that we are going to call pal GPIO low, and pal comes from processor abstraction layer. Its goal is to abstract which microcontroller are we dealing with. And for sure, we will need to pass something to that method that will make us able to address which GPIO do we want to deal with, in this case, to put it to low. But now is when we need to put all our brain cells in action, because whatever we use here that underveils which microcontroller is behind the coroutines, it will counteract its original intent. And unfortunately, most of the hardware abstraction layers provided by most of the vendors are in that way. When that happens, we call these abstractions leaky abstractions. So what can we do? What if we could call this PAL GPIO low and pass a uint8? That will allow us to address 256 independent GPIOs. Maybe it's more than enough. And if we do that, we run the test now. We are passing. And if we do that, you can see that this port stuff, this entity that is on embedded, it goes away. We only have GPIOs. We don't know where the port A is. So now we are going to move each of these behaviors into the PAL GPIO low, one each by each. And as you can see, we are using an if-else. And if you come from the embedded, you are probably thinking about, oh, this is really ugly, and we should be using some kind of left shifting and masking. And you are right, but not yet. Why? Because we don't have corner cases covering this stuff. We will see it later. Now it's the moment where we will do the same with the PAL GPIO high, setting a GPIO to a high level. And let's move it in the same place. So we are not going to put anything else that is covered by the test suite. And we will see how we could evolve later, these PAL GPIOs. But this is the minimum thing that we need. And let's run it into the target. We should be working. We haven't done anything, but who knows? It works. Now, these PAL GPIO methods shouldn't be there. They belong to PAL GPIO module. So let's move it there. Refactor, move. Let's move it to the PAL GPIO that we have pretending that we haven't. We have no PAL GPIO because it's the first time that we use this microcontroller. And we are going to select that these two methods, we want these two methods, PAL GPIO high and PAL GPIO low, to be in the PAL GPIO. Let's move it there. Yes, create the file. It has been created in the entity source folder. We will change it later. Okay. Yeah. And you can see here, these two header files shouldn't be needed the same way that it was before. We can remove them. And let's mark that this include here is because this source file is the only one. The one that knows that we are dealing with this microcontroller. The only one. This is going to be the only one place in the code that is going to be dealing with the special function registers, the port A. It needs to be. So, but if we run the test now, oh, it breaks because the PAL GPIO high is undeclared. And this is because I have been unable to make this seedling deep dependencies to work. It's because it's not being compiled. Let's force the framework to compile the PAL GPIO.c. Now it's compiled. And as you can see, we are in the same place because we don't know what the port, it doesn't know what the port A is. Sure, we are running in the host. It doesn't know what the port A is. So let's move it to green as fast as possible. What about copying these globals and use it there? It should pass, right? Let's do that. And yes, we are in green. Great. But if we go to the BatteryMonitor, this is the module that we want to be, that it should be portable and independent on the microcontroller and the hardware. The line, but in reality, it isn't, because you can see lines 10 to 12 are dealing with the port A, right? So this line shouldn't be there. What if we copy them, remove from them, cut them, and move it to the PAL GPIO.c? The method that knows that exactly this is the microcontroller, only there. And if we do that and run the test again, they pass, and our BatteryMonitor is completely agnostic of the port of which microcontroller is behind the coroutines. The only thing that is missing is to move the PAL GPIO header file and source file to its proper folders. So let's move the header file, the API, to the PAL interfaces folder, and the source file in the concrete implementation for this microcontroller over there. And with that, yeah, with there. Let's run the test again. And it should be passing. Yeah, it does. Let's run it on the target by the very first time, last time. Let's see. Everything is working. Great. We are done. Finished. But let's take a closer look to our dependencies. These are the dependencies when we run on the host. As you can see, the production code doesn't depend on the microcontroller. There is no arrow crossing this hardware boundary because we have inverted the dependency using this abstraction, right? Unfortunately, we have been unable to do the same with the test suite, which is really unfortunate, and we should be doing it because it's crossing this boundary. And the globals, the exactly globals are only present in the PAL GPIO for this microcontroller and not in these source files. When we run in the target, there's no globals at all. It's also we have inverted, as you can see, the dependency, no arrow crossing the hardware boundary on the production code, but unfortunately, the same thing, the test suite is dependent on the microcontroller. We should do the same thing. But just before ending, and you asked me maybe some questions regarding that, incompleteness, okay? Something that I have not shown to you. The BatteryMonitor init, this method, I haven't shown to you, but it should be present. It's the one that allows us to, it's a kind of constructor, but we don't have constructors in C, right? It's an init. It's the way that we say, this is the GPIOs that we are going to use for each of these, for each of these, of the LEDs. Fine. That's one thing. And the other thing I wanted to mention is that probably if you come from the embedded and when you were seeing the part that you have on the left, you were seeing like, oh, this is wrong. Oh, okay. Yeah, it's wrong. The one that you have on the left, you're saying that this is really naive. It's an if-else. It's incomplete. It's not doing the things properly. And you were right. But in order to, and probably you were thinking about something similar to the one that you have on the right now, but probably not so deep, right? Probably not so deep. But in order to transition from the picture that we have on the left to the one that we have on the right, we need to test drive it using its proper test PAL GPIO in order to cover all the corner cases, not only the low level that we have not been dealing with, but also all the ports available on the microcontroller. Yeah, that's the end. This has been my little tribute to a practical technique, which allowed me to start playing to win, as Ken Beck explained in his book, Extreme Programming Explained. Obviously, for sure, we will never be the one like Neo in the Matrix movies, but we certainly deserve much better development approaches to gracefully fly while facing nowadays shifty winds of change. So, time to fly. This is the end.
Thanks a lot, Fran. It was very interesting. I really like the liar anti-pattern. I haven't seen it like that, but it's really like that. You write the test afterwards, like drawing your target afterwards and show that I was on target, but actually you weren't. Thanks a lot. So we have actually a question from Valentina already. Wait a second, I will get rid of that. So what are your suggestions for introducing TDD in legacy embedded code?
Yeah, it's mostly is the same that we do in other realms. We will do some kind of characterization tests, end-to-end black tests, dealing with the special function registers, right? And registering what's going on before touching anything. And later start refactoring without breaking any of this behavior and putting these abstractions in place, these layers. This is for the legacy code that we already have. And for sure, for the new code, try to do it test first, at least test first. Yeah, because TDD encompasses more than only test first, but at least test first. It's the best thing to do it. Well, because I mentioned we were the bottleneck. I have been the bottleneck of the companies during several years. And once we started to do these things, everything changed. We were the ones that were given information to the other department, like, here, the problem is not here. We can look together there, but here it isn't. So it's really interesting, but it's the same. Characterization tests and slightly moving to the proper way.
Interesting point. So since you mentioned characterization tests, what are your suggestions? Maybe what tools or libraries can an embedded team use to write those kind of tests?
For C, I don't know if there is any available, but it could be hard written. It's like written in files, right? For C++, yeah, you have approval testing, for example. This framework, maybe you know, or test or whatever. There are several options out there.
Exactly. So writing those characterization tests and then essentially changing the abstractions. And when you say changing abstractions, could you maybe explain a bit about that? What you
mean?
Mean?
What I mean is like, what usually happens is that our code is reaching several special function registers, which means that it knows everything, right? It doesn't go through any kind of abstraction, right? So for sure, you need to assure before touching anything in a legacy code that is paying our bills, that the behavior is the same. So in embedded, at the end of the road is knowing that we are written in the same order and with the same values to the special function registers in the same condition, right? And if we do that, we need to, once we have that, we can put the proper abstraction in place, like going through this abstraction, hiding the same way I have done with the PAL GPIO, low and high. And once you have that, then you can use a spice or whatever you want. You don't need to run through the deep hardware because you can run everything on the host. But one thing that is really important is that I try to explain that when I started to do it in running the test in the target, because the behavior that is stated in the data sheets is where the manufacturers explain what it should be done. This behavior is there. If you go to a fake in a host, this behavior is lost. So it's really, you have to have a simulator or maybe a demo board. Simply, demo board is not so sophisticated, but run it into the hardware because the contracts are there. I usually say, okay, it's like calling to a database, right? You have to follow certain things in a query, right? And later you can hide the query behind the abstraction. That's the thing. It's the same thing. We are not so special.
Great. Thanks for that explanation.
You're welcome.
So for me, it would be very interesting to hear a bit of from your experience. I mean, when I look at C code, then whatever I see, it's pretty low level. And I'm from your experience, how often do people actually refactor the code?
Well, that's a really good question. It's a really good question. When I presented the tool chain or this tool chain that we have been using in the kata, I say that we were using C Lion, and this is because it's probably not the only one, but for sure at least the one that I know is the best tool that I have found for C and C++ for refactoring. And I will say in my experience, I haven't seen it too much surrounding me, but this is only one kind of the reality, right? It's nothing a real thing. But when you go to conferences and people talk about tooling and which are the major concerns, like build time, or we need weather sanitizers, or we need these kind of things, refactoring is never in the equation. So somehow it means that there's no demand or a really little demand. And this is really unfortunate because it looks like we are fooling ourselves that we are able to do the two things together, make it work and make it right, and also make it fast at once. And there are some people that claims that it's possible. Maybe it is. Maybe there are some person or people that are able to do it, but not me. Everybody should judge if he or she is able to do it. If not, you should iterate and increment. It's the only way to do it. And if you need to do that, you need to do it faster and use some refactoring tools. It's unfortunate. Not too much, Oliver, unfortunately.
Thanks a lot. So would you say that refactoring is maybe not only in embedded, but in general, a bit of a lost practice? I mean, it seems like in the 2000s, it was quite popular with the refactoring book. But now I feel like if you refactor, you're one of few. Is that similar in embedded?
No, it's like if you refactor, you're the one. not the few, you're the one. No, it's even worse, unfortunately. Because I'm not working now in embedded. I work in a backend, let's say, and we do lots of testing and we refactor a lot. But in C, I don't know if it's the tool, the lack of the tools, or the lack of the demand, or both. I don't know which is the root cause and effect. Not sure.
No.
There are tools, and that can be used. Can be done.
And is it a problem, actually? I mean, sometimes I feel like I refactor a lot, and I feel for me the code gets better and I can be much quicker. But I see so many people that are actually so used to non-factored code that they're like, why are there so many abstractions in my code?
Yes, yeah, it is. We get familiar about the landscape, right? The code, and it's like, oh no, I'm going to change it because if I change it, I don't know it anymore. Maybe you should not know it. Maybe you should have the knowledge in test, right? And trust them, right? Yeah, it's what it is. It's like we are working, for example, now with systems that have more than 30 years, and we need to refactor them. They are paying the bills, they are serving our customers, but we need to evolve them. There's no other way to do it. Well, redo everything, but we don't have time for that. It's even worse.
Now on the topic of refactoring, I mean, there's so many things that could be improved. What are your examples of some biggest problems that you've seen regarding code quality?
The biggest one.
Yeah, or the biggest three or biggest five or something.
It's really common, a main God. The main God is like a main that does everything. I have me the first. I have done it several times during several years. Nobody, neither in my technical school, neither my colleagues nor my technical managers, nobody knew anything else. And if you go to some of the vendor examples and technical notes, the things are done in that way. It's like you have the main God, but main God is class God, whatever. It's like everything, for example, 800,000 lines in a single main. Insane. And the funny thing here, I see it as funny, is like people say, no, but doing these things is like over-engineering. And over-engineering is killing all the projects out there. I have not seen that thing anywhere. I have seen totally the contrary. It's under-engineering in the small. But what I see is not the reality. It's only my reality. I don't know.
I would love to see an over-engineered system for once. I always hear the claim that it's going to be over-engineered, but somehow it's what you said. It's under-engineered, not only in embedded.
Yeah.
So would you say that that's solid? I mean, you posted all these words and acronyms on your slides, and for example, solid or damp or dry. Do you think that the knowledge is there, or is the knowledge lacking as well?
I think it is not there. You mean in embedded, right?
Yeah.
I think unfortunately, it's not there. From time to time, people say that firmware is not software. It's like what we do is not software. It's like as long as, for example, solid, right? The principles behind solid is from OO, right? Yeah. Object oriented. but I have applied the dependency inversion principle there. I have inverted the dependency in C. So the concept is the same. The concepts apply to C too, but they say, no, but we are not OO. We cannot do that. Well, it can be done. The concept is there. The way in which you apply it could be different. But first, we should agree that as engineers, the engineering concepts are the same. The solutions could be slightly different, but the concepts are the same. But still, there are people saying, no, but this is not software. This is another thing because we deal with hardware. Yeah, all of us are special. All of us. I deal with hardware. You deal with databases. The other deals with the web or external services. It's the same. Almost the same.
Yeah. Also thought when you showed that actually that it gets pretty close to something like hexagonal architecture, even if you don't use objects and interfaces and all these kind of things.
It is, yes. I don't know if it's an hexagonal, but yeah, it's a layer to a. I haven't shown them, but there are several layers now because I said, okay, that code, its BatteryMonitor is independent of the hardware. It's wrong. It's not true. It's independent of the microcontroller, but it knows that we need GPIOs. So some pings to deal with. But if something changes, because there are other ways, because we don't have more spare GPIOs free, there are other ways to communicate and expand the GPIOs through another basis, low-level details. If that happens, it will make our architecture to fail. And there's an extra layer, right? But under Rails, which is the hardware variant, how are you doing the things? Because the abstraction is something that it doesn't change when the details change, right? And if I say, no, I'm going to change in the way the line is going to communicate with the GPIO or with the LED, and you have to change your architecture, it's because it's wrong. The concept was wrong. It's the same. Yeah, is the onion or the clean architecture or hexagonal, it could be applied. In my previous talk, I talk about it. And also, I explained that we have seen here only a module, but we can also test from the main. You know that in C and C++, well, in most of languages, the entry point is the main. We can do that too. We can exercise main through the test suite directly, and it's an end-to-end.
Okay, great. Thanks a lot for these answers and also the great presentation. Valentina, do you have any last comments?
Yeah, I found this really useful that we covered TDD in embedded and not just TDD in backend and frontend. So it's great to have this spectrum. A really great presentation.
I have struggled a little bit with the time, but I think I managed. We'll see.
All fine.
Okay.
So then we come to a close. So next time on the 30th of October, we have Olaf Thielke talking about how to craft flexible software systems using clean architecture. So it goes into the direction of hexagonal also again. Again, if you want to improve your technical skills, check out our sponsors with the with the QR codes down below. And of course, if you want to keep up with your technical skills development, then keep following us on all the social media. So thanks a lot for being here and listening to Fran's talk, and see you next time. Have a nice evening.
Thanks to all of you.
Bye.
See you. Take care.
Thank you. Bye.
Bye. Whoa.